This is the second video in my series about UniFi switch loop protection. In this video, we will be focusing on STP convergence and its comparison with RSTP. Convergence time means how much time will take for the network to adapt its topology changes. This is my lab environment. I have 3 UniFi switches, ProMax 16, Enterprise 8-port PoE, and Flex 10G. So now they have a very simple topology as shown in the UniFi network controller. If I go to Setting, Networks, you can see for global switch setting for spanning tree protocol, I set it to STP. Based on the current topology and STP setting, if I go to backend for the 3 switches, let's check the port situation. Okay, I'm in for the ProMax 16. Let me first show the port 16's status. You can see a lot of interesting information here. See the path cost is 19. Why is 19? As shown in the diagram, the port 16 is connected to another switch using a 100 megabit Ethernet. So it has a very high cost. The cost will be crucial when it comes to what type of topology will be determined if there's any topology change. Then for this particular part, you can see the port row is designated and the port state is forwarding. Regarding the port state, it's very important for STP. I will talk about them in details later. When it comes to port row, if it's designated, it sends and receives traffic to and from the segment to the root bridge. Then let me show another part, port 17. You can see this part has path cost 2. Why 2? Because it has a 10 gigabit connection. And then the port row is designated because it's connected to a downstream switch. And then the port state is also forwarding. So then move on to the second switch, the Enterprise 8 PoE. For the port 10, the second 10 gigabit port, the row is root. Root means it's the part which is closest to the root switch. So this port 10 is directly connected to the root switch. So that's why the port row is root. And then the port state is also forwarding. The port cost is 2 because it's 10 gigabit connection. Move on to the third switch. For this switch, it's in a similar situation as the second switch. You can see the port row is root because this part, port 4, is directly connected to the root switch. And then the port state is forwarding and the port cost is 19 for the same reason as the first switch because the cable is a slow 100 megabit link. Okay, so this is the current simple port status situation based on the current topology. So now it's time to talk about the port state. After you plug in an Ethernet cable to your switch, if the port starts forwarding packets right away, there will be a lot of problems. For example, it may not know where to forward the packet to. It may forward the packet which shouldn't be forwarded and then cause endless network loop. The way to handle that in STP is the part will go through a series of state changes. Only when it's safe, it will be in the forwarding state. So let's go through them. When you just start the switch, of course, there will be initialization process, and then your part will be in the blocking state. The part will discard all the frames, will not learn MAC addresses, will receive the BPDU, which is part of the STP, but it will not send BPDU. It will only receive BPDU. Then it will go to the listening state. It will still discard the frames. It will still not learn MAC addresses, but it will continue to receive BPDUs, and then it will start sending BPDUs. That means it's is listening. Later, it will go to the learning phase. It will start learning MAC addresses, but it will still discard frames. After a while, it will go to the forwarding state. In this state, it will function as a part is supposed to function. It will forward frames. It will continue to learn MAC address update. It will receive and send STP BPDUs. In any of these 4 states, you can move the part to disabled state. You can do it from UniFi network controller manually, right? In the disabled state, it will not participate in the frame forwarding business at all, and it will not participate in the STP process. Okay, several important numbers are mentioned here. They are about how long the part has to stay in a particular state, and then it can be transitioned to another state. So if you add them up, it's 50 seconds. So that's why you may saw it somewhere else. The part need about 50 seconds to start working. In the current setup, the Pro Max switch is the root switch because I set its priority to the lowest number. So it's automatically elected as the root switch. For each of the 3 switches, it has 2 important parts for this video. As shown in the diagram, only 4 are actively relevant to the current STP setup. Totally, I want to monitor 6 parts. So in the lower part of the screen, you can see 6 Wireshark sessions. So let me start capturing. You can see now among the 6 Wiresharks, 4 of them are showing the STP packets. More specifically, the packet is configuration BPDU. BPDU stands for Bridge Protocol Data Unit. Currently, you only see configuration BPDU because there's no topology change yet. So the configuration BPDU acts like heartbeat packet. Every 2 seconds, there will be a CBPDU sent out from designated part. Just to quickly identify the source for the packet, I already created the coloring rule for the 6 Wiresharks so that if the packet is from the first switch, it will have green color. If the second switch, red, the third switch, yellow. At this moment, you only see green color packet, which means all the configuration BPDU are being sent from the first switch, which is the root switch. Why is that? Because we have a very simple topology, only 2 levels, and the root switch is the first switch, so only the first switch will be sending out the CBPDU. That's why you only see green color. And for the 2 Wiresharks, which are showing nothing, because one of them is for this port 5 of the third switch, the other one is port 9 for the second switch. Neither of them is being connected now. That's why you don't see any STP related packet. By the way, just to show you what's inside a configuration BPDU, let me choose a random Wireshark, click a random packet. You can see here we can tell the protocol is STP, not RSTP. See the BPDU flag at this moment? It is not about topology change. Let's check several important numbers. Remember when we talk about the port state, we mentioned the 3 numbers which are the root cause for the long duration of STP process. So see, they are defined in CBPDU. So for max age, you can see 20. For forward delay is 15. Based on the configuration BPDU, each switch will set the number accordingly. Now we are good with the current situation. Now let me connect these 2 switches with an additional cable so that we will have a loop. So let's see, after I connect this new blue cable, what will happen. I will keep the 6 Wireshark running. Okay, I just connected the blue Ethernet cable. You can see the 2 originally blank Wiresharks are starting showing captured packets. Pay attention to the timestamp. It's 43 minutes, 41 seconds. That's important because we need it to calculate how long the whole STP topology change process will take. Okay, you can see now all the 6 Wiresharks are only showing the configuration BPDU, which means the topology is stabilized. Let me stop capturing. Let's see what really happened. As you can see, now the topology has been changed. We have 3 level switches instead of just 2 level. So let's try to understand what happened. See, for the 6 Wiresharks, I already scrolled to the ones when we start seeing the very first new packet from the new part, which is 43 minute 41 second, right? So then you can see the only Wireshark which also shows new packet is the other side of the cable from the yellow switch, right? That's why these 2 Wiresharks are showing the identical packets. So let's look into this particular one, the one in the middle. And for all other 4 Wiresharks, you can see at the same time, they are still showing the old configuration BPTU. They were not aware of the topology changes yet. So the very first new packet, let me double click it. You can see it's a regular configuration BPDU. See, what's the source? The source is the yellow switch from the 3rd switch, right? So what's the content? It simply says, okay, I want to be your upstream switch and my path cost is 19. Why 19? Because it has the slow 100 megabit connection. So the cost is 19. Then see what's the immediate next one. The next one is from the red switch, from the 2nd switch. What's the content? It's also a configuration BPDU, but it says the cost is 2. Why 2? It's from this 2nd switch perspective, because it was connected to the 1st level root switch by using a faster 10 gigabit connection, right? So the cost is 2. So after the first 2 packets between these 2 switches, they already know what's the best path. But the topology change didn't happen immediately. When it started to happen, see the left side, starting at 44 minutes 05 second, the red switch sent out the first TCN, topology change notification, to the root switch. So if you check the difference between the time when the very first new packet was sent from the new part to the time when the TCN was sent out, how many seconds passed? It's about 20 seconds. Why 20 seconds? If you go to the STP part state change diagram, see the part needs to stay in blocking state for at least 20 seconds. Then it can move on to listening to start sending out BPDU. The red switch send out the first TCN to notify the root switch. Okay, there is a topology change. And if you check the details of the TCN, you can see it's extremely simple. There's no any detailed information. It's purely a notification. After the root bridge receives the TCN, the root realized, okay, there's a topology change. Then what the root bridge will do, see the immediate next packet. It seems to be the same to the packets following it, but if you double click it, see the BPDU flag, topology change acknowledgement is true. So that's why this packet is a TCA for topology change acknowledgement. So which means the red switch tell the root switch there's a topology change, then the root switch responds with a TCA to acknowledge the change. That's it. That's the purpose of the TCA. And then see what's happening after the TCA. Let me click on the ones immediately after it. See, now the TCA flag is no, but the TC is still true. So this packet is still a TC. Then what's TC packet for? You may know the switch can forward the packet to the correct part to reach the correct device because the switch maintains a MAC address table. But if the topology is changed, that means the MAC address table is obsolete. It needs to be updated. But by default, the MAC address table entries need 300 seconds to expire. It's too long. The purpose of the TC is to force the switch to make the MAC address table obsolete in 15 seconds. Why 15 seconds? Again, it's related to one of the configuration, the forward delay, which is 15 seconds. So we talked about what's the purpose of TC, right? And you may notice not only the root bridge send the TC to the red bridge, the TC packet from the green switch also reaches the yellow switch, the third switch. The red switch also send the TC packets to the yellow switch. All of this were captured in the 6 Wireshark sessions. Every switch in the topology will receive the TC, which is propagated from the root switch. So this is the process of topology change detection and propagation. One last important thing to mention, if you try to count the time used for the root bridge to send out TC, so for example for this Wireshark, starting from 44 minutes 05 seconds, then let's see what's the very last TC is at this time. So if you count the difference, it's 30 some seconds. Why the root bridge send out the TC for such a long time? In fact, it's the result of 20 plus 15. The root bridge will send out the TC continuously every 2 seconds for 35 seconds. At the end, see when is the very last TC received? It's about this time, right? And if you compare the starting time for the whole process, you can see the whole STP topology change process took more than 1 minute, more than 50 seconds, which we talked about earlier, which is 20 plus 15 plus 15. The reason is the system needs to do something else. So totally, the system took more than 1 minute to complete everything for this simple 3-switch topology. We are done with STP. Let's move on to RSTP. For the same 3 switches, the same lab environment, the same connection, I only changed the network setting. For global switch settings, I changed the spanning tree protocol to RSTP. So this is the end result. It's the same topology as STP, right? And in the interest of time, I won't show you the SSH backend. I already noted down the results in the diagram. So you can see for port rows, they are the same as STP. And for port forwarding state, at this moment, they are also identical to STP. The only change you can see is the cost, because for RSTP, it has a better way to mark the cost for different physical connections. For example, for this slow 100 megabit link, the new cost is 200K. And for this fast 10 gigabit connection, the cost is 2000. So now let me quickly start Wireshark capturing to see when the topology is stable, what type of BPDU is being transferred. You see similar result. So 2 of the Wiresharks are not showing anything because I haven't connected the link between these 2 switches yet. And for the ones which are transferring BPDU, they are all showing green color, which means they are all from the root bridge, the first bridge. If we check any of them from the protocol, you can see this time is RSTP. It's not STP anymore. And then for BPDU flags, it has more flags. So for this particular one which is being transferred, you can see it says it's agreement forwarding learning. All the packets have the same information. This is the current situation for a stable topology. Now let me do the same exercise. I will physically connect a cable between the red switch and the yellow switch, and I will keep the Wireshark running. Let's see what's the difference for RSTP. Okay, we see new packets in the 2 originally blank Wiresharks. Give it some time. Even though the UniFi network controller hasn't refreshed the topology yet, from the Wireshark, I don't see any special packet. Let me stop Wireshark. Let's see what happened. Let's start from this Wireshark in the middle. It captures this particular designated part for the red switch. First thing you may notice already is the amazingly fast speed for the topology change convergence to happen. See, the very first packet was sent out at 22 minutes 09 seconds, right? See, when it was finished, it's the same minute 17 seconds, which means it only used 8 seconds to complete the whole topology change process, much shorter than STP. So let's try to understand why it's so fast. See the very first packet, it was red color, it was sent from the red switch, right? So if we check the BPDU flag, it is a proposal. This is a very important new flag. So part of the proposal agreement process, which is new in RSTP. The red switch propose, okay, let me be your upstream switch. My cost is 2000. Sometimes you will see the proposal from this yellow switch, but for this particular video taking, we don't see it. It doesn't really matter because it's completely about timing. When the switch receives the other side's proposal, it will send out its own proposal or not, because apparently the yellow switch proposal will have the cost 2000K. Apparently it's worse than the red switch proposal, right? So for this particular testing, we don't see this proposal from the yellow switch, but in the past, when I did similar thing, I did observe this type of proposal. It's all depending on the timing when the switch received the proposal from the other side. Okay, but anyway, the yellow switch received the proposal from the red switch, which says the cost is 2000. And the yellow switch knows if use its own proposal, which will be 2000K. Apparently it's worse, right? Therefore, the yellow switch will agree with the red switch proposal immediately. See the next packet? The agreement is yes. The TC process already started right away. So see, the TC was sent out from yellow switch to red switch, from red switch to yellow switch. They don't wait the TC to be propagated from root switch. That's another major difference if you compare to STP. They will immediately start the TC process. They will refresh their MAC addresses table. Only after 8 seconds, the process is done. Topology is already stabilized. So why it takes such a short time? Why this time we don't see the at least 50 seconds delay before the port becomes forwarding state? As mentioned here in the comments, on receiving the agreement message, the upstream bridge rapidly transition its designated part to forwarding state without going through the listening and the learning states as in the original STP. This allows for faster convergence and reduces the time it takes for the network to become stable. For this particular testing, which means for this particular port 9, once the red switch receives the second packet, which is an agreement to its proposal, it immediately changed the port 9 to forwarding state. Then the packet forwarding can start it right away. So then regarding the TC detection and the propagation, see, we already checked this particular Wireshark. We see the TC exchange is very short, right? And then we can check other switches. For example, the lower part for this port 10, which is connected to the green switch. See, these two switches, the first switch and the second switch, they also exchange the TC. The red switch send the TC to the root switch. Okay, so this is the TC process. It's also different than STP. Overall, the changes reduced the total time needed for convergence dramatically. By the way, for this particular testing, from the Wireshark captured packets perspective, we said, okay, it took about 8 seconds. But it doesn't mean the packets were lost for 8 seconds just due to this topology change, because remember, the system will fastly transition the port state to forwarding immediately, right? So the delay may be much less than 8 seconds. This is the RSTP synchronization process for this simple 3-switch topology. This is the end for this video. Thanks for watching.